So, hi everyone, my name is Paulo. I work at one place called NIWA, which stands for National Institute of Water and Atmospheric Research. That's such a mouthful, I know. My title over there is HPC and AI Architect, and today I'm here to talk about high performance computing on AWS. So this is the agenda for today. I'm going to give you a crash course on high performance computing, in case you don't know what it is, and then I will try to translate that into AWS terms, and then we're going to have a demo. So if you want to jinx it, please don't. That's not a recorded demo, that's a live demo, and everything can go wrong. The most important thing is, I'm not assuming that you know anything in particular, so I will talk about difficult concepts and technologies that you may have never heard before, but I will tell you everything that you need to know in order to follow that presentation. Without further ado, what's high performance computing, or HPC for short? So it had historically used supercomputers in the past to solve advanced computational problems. Nowadays, you can use both supercomputers or computer clusters and still be called the same. And the term is mostly used for scientific research or computational science. So if you haven't heard of HPC before, that's probably the reason why. But that's a big deal, and that's what I do for a living. So the first question that someone may have is, what is a supercomputer in simple words? So a supercomputer can be defined by one or more racks of nodes in a data center. So show of hands first. How many of you have seen a data center in person? Oh, that's actually much better than I thought. Awesome. So you know what a computer rack is, right? If you don't, a computer rack is that metal structure over here. So you have like a row full of them and a guy that pretends to be doing something about it. That's an incredibly noisy environment to be in, and that's really, really cold, right? That's all you need to know about what a data center is and what a rack is. Also, a supercomputer contains tens of thousands of processors. So that's the first thing I need you to memorize. The second thing is, nodes are interconnected using a high-speed network. That's crucial to remember. It will come in handy in the next few slides. And a supercomputer is usually used for data-intensive and computational heavy process, such as quantum mechanics, aerodynamics, physics simulation, weather forecasts, and the list goes on. So anything that requires a lot of horsepower to calculate the end result, that's a good candidate for a supercomputer, essentially. One thing that's very different from regular computers is that in the world of supercomputers, we measure the performance not in how many instructions can be executed per second. We're not too interested in that. We have a different metric, which is called flops, floating point operations per second. So, show of hands again. How many of you know what a floating point is? Okay, awesome. That's good. So, any number with the decimal digits is a floating point. So, 1.5 is a floating point. 1 is an integer. So anything that you can count, the digits after the comma or after the dot, that's a floating point. Okay? That's all I need you to know right now. What a supercomputer looks like. And this one has been released not a long time ago, possibly 6 months ago. And that's the third most powerful supercomputer in the world. And here's the problem. It's not that impressive when you see it like that. It's just another set of computer racks with a bit of skin out there, which is what you get when you spend millions of dollars on those computers. So it's not good enough, but this thing is magic. And I will show you in a minute why that's magic. But an example closer to home will be the one that we have at NIWA. So at NIWA we have many data centers operated by ourselves. This is one of them, and each row of that is a different supercomputer. To give you an idea of how powerful those computers are, and bear in mind, that's an old supercomputer. That one has been bought in 2018. We have around 8,000 cores, 32 terabytes of RAM, and the number of floating points per second that we can calculate is around 300 million. And that's an old one. It's really, really old. So the one I'm just showing is just that one on the left-hand side. So there is 7 racks of supercomputer. So there are more. Now, here's the biggest challenge that I have. When you talk about supercomputers and you just show a picture of them, it's really, really hard to grasp. What's the difference between a regular rack and a supercomputer? So I thought that I should give you an example. So let's start with the numbers first, and then I will translate that into something that you can imagine. So a general purpose computer, which is what you have, what I have right here, or what you would get on a cloud provider, can give you from 10 to the power 11 flops all the way to 10 to the power 13 flops, okay? And then on the supercomputer side, we can get 10 to the power of 17. And before you zone out, let's use an example. So imagine that every flop is actually a grain of sand, okay? So let's start on the left-hand side, and we're gonna go with the lower bound. Oops, my mistake, spoiler alert. So 10 to the power of 11 grains of sand put together side by side would give you a line that would stretch between Auckland and Lake Taupo. That's around 200 kilometers. Just bear in mind that each grain of sand is around 2 millimeters wide, okay? That is a lot of grain of sands, I understand that. But 10 to the power 13 grains of sand put in the exact same way would actually give you a line which could stretch from the South Pole all the way to the North Pole and start making its way back. That's a general purpose computer. And that's good, and it can do that every second. Now, 10 to the power of 17 can give you a line that would stretch between the Earth and the Sun. That's how different they are. And the reason why we need those examples is because human brains have been wired in a way that we can't really imagine big numbers. So if I ask you to imagine the distance between the center of our galaxy all the way to one of its extremes, you can imagine, but if that would be wrong. And if I tell you to compare that distance to the size of the universe, you would imagine something big, but that's still wrong because we are not wired to imagine big distance. So I hope this example gives you an idea of the difference between these two compute powers. Now, that we have a big toy, a very expensive toy, which is around $1,800 million. No, just kidding. Just $18 million. But if I happen to work in a company that has a high-performance computing cluster, what would I find? So essentially we have ourselves. So let's start simple. And then we would go to something called logging node. In other fields, this is called bastion node. It's essentially a machine that is not connected to what we want, but it allows you to perform certain activities. Which activities are those? So the first one that we can do is we can get our source code, our inputs, our data that needs to be processed by the supercomputer, and push that to a file system. That file system also needs to be extremely fast. That's why it's called high-performance file system. But the important part here is it needs to be self-contained. The second most important part here is this machine does not have access to the supercomputer. And that's for security reasons. Because a supercomputer is really expensive, you cannot have many of them. So you have to be extremely careful with the way you expose it to the world, because if one of them is down, it will cost you a lot of money. So that's one of the few things I need you to keep in mind, because that dictates how this whole ecosystem can evolve, right? Second thing, from the logging node, I need to communicate with another machine, and that second machine does have access to the supercomputer, called Workflow Manager. But for all intents and purposes, we can call it Scheduler, okay? So what this machine basically does is it gathers information about the job that you want to execute on the supercomputer. So it needs information like, where is my code residing? How many nodes do I need? For how long do I need those nodes? So information like that. And this one will keep a database of tasks to be scheduled on the supercomputer. Again, for the same reason, you don't have many supercomputers. So what you can do is to find ways to best utilize the resources you have. So scheduling is a way of actually making sure that your supercomputer is utilized to its full potential. So the scheduler will try to find gaps in the job planning of the supercomputer and try to squeeze your request in that. Okay? Now comes, the star of the night, the supercomputers. Essentially, there are two important things here. The first one is, when a supercomputer gets the chance of running your job, it will fetch all the metadata, like what is the source code and where it lives and all of those things, and basically download it from the high performance file system and start executing it. And it will execute until the following conditions are met. Either your job is done, or your job has failed, or your job has expired, or another job with a higher priority has taken place. Whatever happens first, okay? And last but not least, is crucial, really, really crucial, because we will talk about that you understand that these worker nodes, which the combination of them, you can call it supercomputer, they are interconnected using a high-speed network, which means that your job, if you say that my job requires 2 nodes, it's a lot of processing power, your source code that will run on those nodes will have to orchestrate how to break down the tasks that you have to process and how to communicate the results back and forth between nodes. So that's all your responsibility. The only thing you actually get for free is the chance of running your code on a very powerful machine, okay? Which is very different from what we do on cloud native applications, I understand. But the more you think about that, the more you realize that this makes sense. I'm not saying I like it, I'm just saying it makes sense. Now, let's translate that into AWS terms. So I think that the best way we can do is we get piece by piece and start translating them individually, so I can give you some of the options. So let's start with the high performance file system. As you can see, that's the only point in common between the logging node and the supercomputer cluster. And make no mistake, this is not something simple. This deserves a presentation in its own right. But for today's presentation, you need to remember 2 things. If you remember that this shows up on both the logging node and the supercomputer nodes as a shared folder, you're good to go. The second thing you have to remember is that there is no ultimate solution for it. So there are many leaders in this field. So IBM is incredibly strong in that field. They have one offering called GPFS or elastic spectrum scale, and they keep changing the name to make us really confused, but that's a very interesting technology. Also, a high-performance file system is not a single machine. It's a cluster of machines that will get read and write requests and split that into as many ways as you configure it to be split into, and try to process those requests in parallel. That's why that's a high-performance one, okay? There are, of course, many performance considerations that you have to take into account if you want to extract all drops of performance you can get out of that. But for today's presentation, we're not gonna get into that. If you want to talk about it, I'm more than happy to talk about that after the presentation. But in AWS terms, one thing you can count on is a product called Amazon FSx for Lustre. So that's a high-performance file system, which basically they will set up a cluster for you and give you the instructions to mount that into the machines that you are interested in. And the most interesting part is that this cluster that they set up for you use very sensible default values. So in most cases, you don't have to tune it, but you're also given the flexibility to tune in, so you can make that a bit more specific to your use case. That requires a lot of analysis from your side, but you can do it. And that's the key takeaway. It's not a solution that works for you, and then if you change your workload, you're stuck. No, you can change it so it keeps working for you. Okay, with the high performance file system out of the way, we will talk about the logging node and the scheduler nodes. They are both general purpose virtual machines, and the reason for that is because there is nothing special about them. They're just regular servers. They do have special purposes. For instance, the logging node needs to be hardened from a security standpoint because that one is available on the internet. So you want to make sure that it's as close as possible to unhackable. It's impossible to get to that point, but you want to make sure that you make it really, really hard for other people to do bad things with it. The second part is the workflow manager is also not that special as long as it has access to a database, so it can actually collate together all the requests that has been sent to it. It will do its job. So in that case, any EC2, which is the compute service from AWS, would actually do the trick. But for completeness argument, or completeness sake, when you create a EC2 on Amazon, you can choose between these different instance families. And what that means is each one of them will run against a different type of hardware in which you can get different types of performance out of that. So because, like I said, because this one is not, there is nothing really special about it, I would definitely go with the general purpose. But yes, there are use cases in which you may need the other ones. But we're not here to talk about EC2, we are here to talk about supercomputers. So let's move on. Let's talk about the star of the night, the supercomputers. And spoiler alert, that one is going to be slightly harder, but hang in there. I promise, it's going to be worthwhile. So the first thing is, you know that if you have a machine that has to be an EC2, there's no other way around it, okay? Actually, there are, but not for supercomputing purposes. So we do need an EC2. But the question is, what EC2 would be relevant for a HPC environment? And if you have a sharp attention to detail, you have noticed that we have one instance family called HPC optimized. Now, what makes a HPC instance family a HPC instance family? Like, well, what is the difference? I think that's a fair question. And although the projector hasn't been really kind with me right now, I'm so sorry about that, there are two things you have to pay attention, and I'm gonna read it out because I don't think you can read it from back there. So these are the only instance families in the EC2 offering that gives you an offering by cores rather than vCPU. Two things you have to understand for the purpose of this presentation. The first one is cores is the physical cores, while vCPU is the virtualized version of that. And the second one, which is a bit more juvenile, but I think that it will fit for today, is CPU cores trumps vCPUs. Okay, that's all you need to know. Second thing is EFA network. Now, we will talk at length about it, but you have to understand that EFA is the ability of actually connecting different nodes using a low latency network. And the combination between a low latency network and physical cores is what you can call HPC optimized. Okay, that's why the other ones are not, they can be used, but they are not as fast as these two. Okay, but this doesn't solve the problem in 100% of cases. There is more to it, and this is where I need not only all of your attention, but also all of your imagination. Remember that I told you about that a supercomputer requires a internode high-speed network. How can we do that in AWS? Because yes, we can choose instances that have, you know, they are optimized for I/O. We can choose instances that are optimized for other types of communication. But how do I ensure that my nodes can use a low latency network between them? And that's actually my favorite point, because I'm usually poking the wound when I talk to people who are not, from the cloud world. So if you talk to someone from HPC world, they are almost emotionally attached to this technology called InfiniBand. Okay, so if you get InfiniBand out of the question, let me explain the problem it solves first. So if you have application number one on the left-hand side, and application number one needs to send data to the application number two, the only possible way without InfiniBand is application number one sends a request to the operating system and says, this is the data I need to send. The operating system, depending on how many tasks it has to do at one given point in time, will eventually send that request to the network card, which will traverse how many hops it actually requires, all the way to the point that it gets to the final destination, which is a different hardware, and then the packet would actually make all of its way back to the application number two. And here's the interesting thing. Everything that you have between sending the data from application one and receiving the data on application two can be called overhead. And honestly, you do not want that. But there is a reason why we do it. Our field has evolved in such a way that security takes a higher precedence over performance. If you have to choose between them, security it is. Okay? So isolation and security is actually the thing. Now, for high performance computing, you need to find some sort of common ground in which you can find a shortcut between these two applications without compromising security so much. And that's what InfiniBand is all about. So you get a proprietary protocol using a proprietary hardware and a proprietary router that can send up data from application one all the way to application two, but bypassing the operating system. So your overhead is much, much smaller. And that's how you achieve a high-speed network. And that's amazing, but that's proprietary, which means that you have to use some of the things they allow you to. But most computers, or supercomputers out there, or even on-premise data centers, they rely on this quite a lot. And if you asked those people back in the day, why didn't they move to the cloud yet? Their answer would be straight away, because cloud doesn't have InfiniBand. That's their default argument. Now, what do we have on AWS? We have one thing called EFA, which stands for Elastic Fabric Adapter. It basically allows inter-node connectivity with speeds up to 200 gigabits. There is one thing important to emphasize here. This is not the same as InfiniBand, because it uses a different approach, but it addresses some of the similar problems, okay? So essentially what it does is you have to install this library on your operating system, and this library will actually bypass the operating system and eventually get to the device, which is roughly how InfiniBand works, but it's not exactly the same. But you get the same end result, and that's what matters, okay? So second thing is out of the way. We need HPC instances and an EFA between that. Are we done? We're not, sorry. We have another problem. And this is a very fascinating problem, actually. So here's the thing. When you get to a scale big enough, you realize that some of the assumptions you've made so far start falling apart. But the interesting part about that is you can solve problems using first principles, which is such an interesting way. So let's put it this way. If I get a single computer, the way I calculate how fast a computer is by basically saying, can you process this and tell me how long you take to process that? That's easy. When I have a cluster of computers, you realize that not only the individual compute power is important, but the ability of them communicating with each other is equally important. So you increase the number of dimensions that would give you a higher performance. And that's really interesting. Now, there is one problem that we have never solved, and unless I'm told otherwise, I don't think we will solve that, which is we cannot make anything move faster than the speed of light. I'm so sorry about that. Maybe there is. I don't think there is. But technically, we know that if there are two things which are really far away apart, it will take longer for the information to traverse from point A to point B. But if they are sitting closer together, it is not going to take as long. So essentially what I'm trying to say is that the way to make your supercomputer more powerful and faster is actually to pack all of those instances tightly together. Which is kind of like, oh, okay, this is obvious. But believe it or not, it's not that obvious. And I will tell you in a minute. But look at that. How do we do that on AWS? So we have one feature called EC2 placement groups. There are three options. The one that we really care about is the first one. But essentially, that's a parameter on the API that you can specify to the EC2 service what you want the EC2 service to take into consideration when finding the place to place your instance when you launch it, right? So the first one is called cluster placement group. What you're trying to do here is to say, I want my instances to sit physically close together, possibly even sharing the same hardware. You have no guarantees that this will happen, but there is a good chance that this can happen. Okay, so you're reducing, the distance between point A and B. There is another one which is the complete opposite of that, which is called spread placement group. In this particular case, you are saying, whatever you do, do not place it in the same hardware as other instances that I have. And that's definitely good for high availability scenarios, but most people don't care too much about it unless you have something incredibly mission critical. And the reason for that is because if you don't specify anything, you know that your you have an application which spans around 3 different data centers. Statistically speaking, you have a bigger chance of actually sitting in any of those data centers, but not in the same hardware, much bigger, right? Than actually sitting on the same hardware. So if you don't specify that, technically you kind of get the same thing as the spread placement group, but if you specify that, you're just giving the EC2 scheduler one more constraint that says you cannot use the same hardware at all, okay? I don't see many people using it, but they should. It's a pitching, but there is something halfway in between, which is called partition placement group. This one is slightly harder to explain, and the reason for that is because there are not many use cases out there where people make use of it, but I'm sure that you know some applications that would greatly benefit from it. But before I tell you the name of those applications, let me tell you what it is. So the partition placement group allows you to specify different partitions, and each partition can have one or more virtual machines inside of them, and instances inside of the same partition can share the same hardware, but instances in different partitions will never share the same hardware. So good examples will be a Kafka cluster, because each topic could be set to a different partition. Or if you're dealing with big data, a Hadoop cluster. So if one of your partitions fail, your Hadoop cluster will actually retry your job on a different partition, and you get the final answer without actually having the whole job failed. So there are a lot of applications that can benefit from it, but people don't usually use it. It's a pity, but this requires a bit more of an explanation of what you have to change on your application in order to make use of it. If you want to talk about that, I'm also available after the presentation. But for completeness sake, you know, those are all the options available. The one we care is the cluster placement group, after all. All right, now we have the bare minimum supercomputer architecture on AWS, which takes us to the demo time. Ooh, and like I said, I haven't recorded that, so wish me luck. All right, so here's the thing. I'm connected to one machine, which is the scheduler node or the logging node that you saw in this one, okay? And what I have already done, in the best interest of time, is to get my application and all of its dependencies, and I pushed to the file system here, okay? So that file system is actually mounted. Let me see if I can actually grab shared. There we go. That file system is mounted on oh, you probably can't see it. Let me actually set title. Text in terms of size, font, custom font. There we go. Oh, that's probably better. Even I could watch it, could see that. Okay, so my Luster.fs, which is the high performance file system, is mounted on /shared. So if I get there, what I could see is a bunch of files, because I'm not that organized. But the important part is, let's start with the hello world one. So what I have here is a script that doesn't do much. It sleeps for 30 seconds, and then it echoes hello world from whatever node is actually running against, okay? So just gonna give you an example of how to run a node in multiple computers first, and then we're gonna run, you know, the actual example. Now, before I actually do that, I think I have another thing I would love to do. So how do I know which nodes are part of my supercomputer? So the scheduler that I have access to is an open source one called Slurm. It's very old. No one likes it anymore. AWS has a much better one called AWS Patch, which can do roughly the same, but this one is open source, so HPC people like it for some reason. So when I type S-info, S for slurm, and info for information, it will tell me, you know, which partitions I have available. And the interesting part is it's telling me that I have up to 64 nodes in my supercomputer cluster. So I can choose, from 1 to 64. I could specify the partition if I wanted to, and if I had many partitions, when I launch a job, I could say, I want to run my job on that partition because maybe that partition has machines with GPU and I want to use GPU. So people in the scientific community, they know exactly which partitions are mostly used or which hardware characteristics they would find on different partitions. Once you submit your job, you can actually type SQ, slurm Q, which will give you an idea of how many jobs are running concurrently at any given point in time. Now, this command here that I have is trying to do the following. It's saying, I want to run a job on 2 nodes, and on each node, I want you to run hello world.sh, which is the file we just saw, which essentially will print hello world, okay? Before we do that, I just need to double check one thing, because that's a live demo. That's how things work. So that's my AWS account. Yeah, that's what I thought. Actually, that's really good. I think you guys got lucky, because if everything was already up and running, you wouldn't see that happening. So technically, even though my cluster says that I have 64 nodes, you can clearly see that I just have one instance, which is the scheduler node, right? Essentially, when I run this, it will tell me the job has been submitted and its ID is number 3. So if I actually query that, it will tell me that job ID number 3 has this CF status, which is kind of like a creation status. What we could see, and unfortunately this will take a few seconds, I'm so sorry. Oh, there you go, it's actually better than I thought. It realized that I need 2 jobs to run that, and my scheduler thought, okay, it's time for me to launch, new nodes. And those nodes will come pre-configured and hardened as well, so it could run my application without any problems, as long as all the dependencies are within the shared file system. That's the only criteria you have to abide by. You cannot expect anything to be installed on the supercomputer cluster, because it's meant to be used by so many people, so nothing will be installed there. That's an ephemeral place. Yes?
You ask now or at the end?
I will probably after, but you have already raised your hand. I don't want to be rude.
That's okay. So I was asking, so that these tools where you specify their job, like when you said SBatch and SQ, so are these like, is it a tool like that you manually installed on that machine, which is the login machine?
Could you repeat the question? I'm not sure if I got it.
So what the SQ and SBatch, or are these like some kind of commands that come out of the box, like?
Okay, very good question. So this machine here, which is the workflow manager, I installed before this presentation the Slurm scheduler. So that's something I did, behind the scenes, and that's where the SQ info comes from. Yeah. So there are other schedulers out there, but the Slurm one is very interesting because since it uses the bash script syntax, it integrates really well with a lot of tools we have in the ecosystem. So the integration barrier is much smaller. That's why it's the preferred one. Yeah. Yes.
Did you use the predefined MI image, or you install all the stuff by yourself?
I installed everything by myself. Let me see if I can show you. Yeah. So these are the installation processes I've run myself. So I'm basically, in the supercomputer world, usually because you have a big affinity with the hardware you have, because it's not going to change, you install very specialized compilers that can use better heuristics to optimize your source code to run as fast as possible on the hardware that you use on your supercomputer. So in this case, because I knew I was going to use Intel machines, I installed, for instance, the Intel compilers, the EFA fabrics, and everything else. So I oversimplify things, but just to make sure that we could finish the presentation in 1 hour. Any other questions? Okay, awesome. So let's see if that has already run. Yes, it has. Let me see if your memory is sharp. What was the job ID number? 3. Ah, there it goes. You guys are paying attention. Amazing. And what is the output I'm expecting? Hello world, and what else? Ah, there we go. You guys are the best. And there we go. So I have 2 hello worlds, which were collated, by the output of that executed in 2 different nodes. And because I printed the host name, I know exactly which one came from which node. Okay, that's the simplest example I can give you. There is something a bit more advanced that I would like to share with you, which is the simple use case. Terrible name, I know. This one is slightly more complicated, and what it does is it calculates the temperature and the precipitation of the world, the entire world. Okay. There is one thing I have to admit, which is I didn't get access to the most powerful compute node I could. So my plan was to actually run that and wait for 5 minutes so you could see, a weather forecast happening in real time. And because I didn't get that very powerful machine, we will launch it, and then I will show you the end result, because otherwise we are going to have to be waiting for the results for hours. But this is what it looks like. So the first few things I want you to pay attention to. So the first one is, probably is not a good place for you, sorry. So the first one is, at the top, I'm actually specifying the number of nodes, how many threads per node. So in this particular case, there will be 32 instances of my program running in parallel across 2 different physical nodes. I'm specifying where it should, start executing it from. So all of this, even though it looks like comments, they are actually metadata for this Learn scheduler. So it just tells this Learn scheduler how to place it right. At the bottom comes the interesting part. There are a bunch of things I don't want you to worry about, but I want to emphasize a couple of things. The first one is I'm loading dynamically the lib fabric. As I said, we cannot expect anything to be installed on the supercomputers. So everything that needs to be done prior to executing your job, you have to put that on your job execution. And the second thing, I'm specifying that I want all the communications to happen via EFA, which is our InfiniBand-like interconnectivities. And at the bottom, I'm essentially just saying, look, just execute it. That's a very oversimplified way. I don't think it's relevant for us to dig into what each one of those programs do, but as long as you know that it crunches a lot of data, we're talking about billions and billions of rows, and it can do that in a few hours. That's amazing by itself. Now, what we do is we do sbatch, and I forgot the name of that. I'm so sorry. What was the name of that again? It was Learn UFS. My mistake. So basically do this, and that's how I'm specifying to the supercomputer scheduler what I want it to run. So the job has been submitted. This will take a long time. Don't care. Let's not worry about that. But the end result will be this, which I think is probably a bit more relevant. So, so this is what the temperature would look like across the planet. That's using Kelvin, but not important. The other thing would be the precipitation one. And those are the places that will potentially rain at. So, all of those things are very interesting, and technically those things are mission critical because it can save lives. So I think it's very important in to think about, you know, the role of supercomputers in our society. We cannot forget that because supercomputers started a long time ago, a lot of its tools and algorithms are very old and old-fashioned. So I do agree with you that if, like me, you come from a cloud provider background, you could imagine ways of actually spreading this algorithm into distributed nodes across distributed data centers to actually get you the same answer. I do not disagree with you. I just want to emphasize that there are two things that are worth noting here. So the first one is those algorithms have lots of heuristics of a lot of people that even have probably died by now, because we have been doing this for a long time. So a lot of those things are hard to come by. So if you want to refactor something like that, it will take you a long time. So it is possible, but it takes some time. I think that's the bottom message, the bottom line message. The second thing is anything that has used a very constrained ecosystem like supercomputer is right now. So we use batch processing models. You get a chance to run and you try to make the best out of it, right? So all of the tools that scientists and developers rely on are based on that model. So the ecosystem needs to keep up with the new technology advancements before scientists can actually make use of it. But that's a very fascinating thing as well, because if it's for research institutes, talking about cloud computing, for them it is a new thing. It's like talking about cloud computing 15 years ago or 10 years ago. People are like, what you talking about? What's a cloud, right? So it is like traveling to the past, but you have, you know, the ability of actually, you know, making the difference and potentially giving society as a whole different ways of using even more computational power to calculate those things with even more precision, so we can save even more lives. So I think it's a very interesting place to be. We are hiring, in case you're wondering. We're hiring. We want people with cloud computing experience, because NIWA is in the process of actually migrating to the cloud. It will take a little bit of time, which is frustrating for me, but we will get there, and probably we're gonna need a lot of people. Anyway, now comes my favorite part, questions.
Quick question. When you submit the job
Yes.
for the supercomputer, so how long does it take for the code to be up and running?
Which one?
The first job, you submit this